The Sun is a star, a great globe of seething hot gases, 864,000 miles in diameter and 93 million miles from the Earth. By means of the tower telescopes of Mount Wilson and the coronagraph of Harvard College and University of Colorado High Altitude Observatory, we will study the Sun in detail. All living forms on Earth depend on the Sun's radiation. It is the most important astronomical body that we know. Mount Wilson Observatory is located on a mountain terrace a short distance from Pasadena, California. The 100-inch reflector, one of the largest telescopes in the world, is housed in the large dome which you see as we fly over the observatory grounds. The smaller dome houses a 60-inch reflector. At the top of the two towers are mirrors which catch the light from an object and reflect it to cameras and instruments in the operating rooms below. They are used in studies of the Sun and constitute the Mount Wilson Solar Observatory. Total eclipses of the Sun occur when the Moon passes exactly between the Earth and the Sun. We will now watch a total eclipse from beginning to end. Observatories and scientific organizations send expeditions to any part of the world where a total eclipse is to be visible for photographing and observing these astronomical events. Such observations and photographs are highly prized and give information that cannot be obtained at any other time. As an eclipse progresses, the sunlight is gradually cut off, and the effect on Earth is similar to twilight. The light assumes peculiar hues and shades. Just before totality, the thin remaining crescent on the Sun is cut by high mountain peaks on the rim of the Moon. The blaze of light coming between the peaks causes the diamond ring effect. This slowly fades, and the inner corona is seen, with Bailey's beads, similar bright areas, around the Sun's rim. The chromosphere flashes red for a few seconds, and when the full face of the Sun is covered, we see the spread of the beautiful pearly corona. In this eclipse, the corona extended for more than 1,000,000 miles. This pearly glow is caused by the Sun's intense radiation across this region. Totality usually lasts for 1 to 3 minutes. The maximum in any eclipse can last about 8 minutes. The chromosphere is a region several thousand miles in depth. It takes its name from its rose-red color. This is a seething, swirling region of very hot gases, and the flame-like prominences are great gas explosions. They're a very interesting feature of a total eclipse. From this swirling region, explosions blow out in great bomb bursts. This is the hydrogen region. The coronagraph at the High Altitude Observatory of Harvard College and University of Colorado creates an artificial eclipse and enables us to observe these hydrogen explosions which occur throughout a wide equatorial belt of the Sun. The gravitational attraction of the Sun is 27 times that of the Earth, and the material blown out in these explosions falls back to the surface in a great deluge. Regions of magnetic disturbance draw some of the material sideways for thousands of miles. The great hydrogen explosion on the right blew out more than 100,000 miles. Much of the material is drawn sideways to the left by one of those great pools of magnetic disturbance. Great mushroom heads rise 50 or 60,000 miles. And here again you see the material raining back to the surface, very much as it's seen in photographs of the atom bomb on the Earth. Flares are regions of intense atomic activity. When they're pointed directly toward the Earth, they interfere seriously with radar and radio communications, blotting out in the short wavelength sometimes for hours and occasionally for 2 or 3 days at a time. This flare was 60,000 miles in length. At one end, there's a great pool of magnetic disturbance drawing material from an explosion that occurred far over to the left. Sometimes great bubble-like arches blow out. These break in the center, and the material pours back to the surface. Then there are great mushroom clouds, like the atom bombs on the Earth. Thousands of tons of material blown out in these great explosions. This one went to a height of 100,000 miles. Here we see one that blew up more than 200,000 miles. Then a mushroom-type explosion, like our atom bombs. From this display, we gain a definite idea of the enormous energy of these hydrogen explosions on the Sun. Great arches sometimes blow out several 100,000 miles. By slow motion views, we watch one of these hydrogen explosions rising 135,000 miles in 4 hours. At 9:30 in the morning, its height was 35,000 miles. The great mushroom head spread out to a width of 100,000 miles, and at 11 o'clock it seemed to break loose from the Sun's surface. It rose about 100,000 miles. Then connecting again with the surface, it rose as a great curved column, reaching a height of 170,000 miles at 1:30 in the afternoon. Some of these great gas explosions seem to be connected with sunspots. As several sunspots come to the limb or rim of the Sun, we see great explosions in profile, indicating that sunspots are regions of very violent activity and energy radiation. Sunspots occur in a cycle of about 11 years. There's a variation. The period is sometimes shorter and sometimes longer. Some sunspot groups are very large, covering an area of several 100,000 square miles. This close-up view gives a better idea of the great size of some sunspots. The small dot at the top of the field shows the relative size of the Earth compared with the area of this large sunspot group. By watching a group of sunspots for 4 consecutive days, we note that the changes are very rapid. Sunspots usually persist for only a few days, although there are occasional groups that remain active during an entire rotation of the Sun on its axis, which is 25 days at the equator. The rotation is about 33 days near the pole. This indicates that the Sun is a great globe of gases and not a solid body. The rotation of the Sun is shown by sunspots, which we watch for several days. They appear at the left, along the rim, and advance across the Sun's disk as it turns on its axis. Viewed with ordinary light, we see the rice grain appearance of the Sun's surface. By attaching a spectroscope to the telescope, we can analyze the Sun's light. Using the spectroscope, we admit the light through the hydrogen alpha line of the spectrum alone and see the sun's hydrogen layer. Then we admit the light through the calcium K line, and that reveals the calcium region. By observations with the spectroscope, we detect the various chemical elements in the sun and gain our knowledge of the sun's composition and structure.